Well, hello, ap2. It's time for chapter 10, part 2. We're going to be doing a little bit of history and playing around with pressure, volume, and temperature. So the first thing I want to talk about is Boyle's law. We want to talk about Boyle's law. I forget the year, but I want to say it was roughly 1660. We can look that up later. Roughly 1660 anyway. Boyle noticed that there was a relationship between pressure and volume. He noticed that if you held the temperature of something constant, that pressure and volume were inversely related. Boyle noticed that pressure was proportional to the inverse of the volume. If you apply pressure to a balloon, the balloon gets smaller. If you squeeze on it, it gets smaller. So there we go. This in turn means that the pressure times the volume is constant. Another way of writing pressure volume is constant is to say P1 V1 has to equal P2 V2. That remains constant. That is Boyle's law. Well, the next thing we want to look at is something called Charles' law, named after Charles, who was French, so it's probably pronounced Charles, but this is America, so I'm saying Charles. Charles, I want to say the year for this was roughly 1800. Again, we can look that up, but that means like 140 years went by. Man, you can't accuse physics of going quickly, that's for sure. At any rate, Charles noticed that at constant pressure, that volume was actually proportional to temperature. If you heated something up, it got bigger. If you cooled something down, it got smaller. So that's Charles' law. Another way to say that is that the volume divided by the temperature has to equal a constant. Another way to say that is that volume 1 over temperature 1 has to equal volume 2 over temperature 2. This is Charles' law. Well, a really interesting thing happens. If you combine Charles' law and Boyle's law, you get what some people call the combined gas law. But to me, if you combine Charles and Boyle, you end up with Choyle's law. Anyways, combining the two says that P V over T is constant. Another way to write PV over T is constant would be to say that P1 V1 over T1 has to equal P2 V2, oh that was a bad V, V2 over T2. So either way you want to look at it, whether it be this way or this way, this is the combined gas law, our so-called Choyle's law. Okay. Well, what's this constant all about? What is this constant? What is this constant? What does PV over T actually equal? Well, the constant is NR, where little n is the number of moles, everybody's favorite unit, the mole. You can read in the textbook for the definition of moles if you happen to forget it. This thing right here is the ideal gas constant. Yes, our constant is equal to the number of moles times yet another constant. As a reminder, the ideal gas constant, R, is 8.31 joules per mole Kelvin. Okay? Well, as it turns out, that constant can be written another way. Moles, that's the favorite unit of chemists. In physics, we tend sometimes to want to do more of a statistical approach, and in the next lesson, you're actually going to see such a statistical approach. We actually tend to want to deal with the number of particles instead. So, as it turns out, the constant nr can also be called capital NK, where capital N is now going to be the number of particles, so not moles, this is now the number of particles, or let me get rid of that, or particles, and K is called the Boltzmann constant. The Boltzmann constant. And K has the value of 1.38 times 10 to the minus 23 joules per Kelvin. So, as I said, whether we like NR or capital NK, it's the same unit, it's the same value. So, what does that give us? Well, it means that we can write that PV over T equals NR. We could also write that PV over T equals NK, which gives immediate rise to our ideal gas law. Either of these is the ideal gas law. Puvnert or Pugnicht, whichever you prefer. At any rate, at this point in class, we'll start solving a couple of problems, so I'll see you then.